So the components of an electric system dissipating 180 watts are located in the 1.4 meter long horizontal duct, whose cross section is 20 centimeters by 20 centimeters. The components in the duct are cooled by forced air that enters the duct at 30 degrees C in 1 atmosphere at a rate of 0.6 meters cubed per minute and leaves at 40 degrees. Determine the rate of heat transfer from the outer surfaces of the duct to the ambient. All right. So I don't need to copy that. So let's go ahead and write givens. We got T1, 30 degrees C, P1, which is 1 atmosphere, is 101,325. Oh, this is kind of crazy. Similar stuff we're doing in the first fluids, right, students? Some of you guys?
And we can flow past at the same time. That'd be like good.
I asked Wesley, Heath, anybody else?
Just stuff that. But I feel like they kind of coincide with each other as well. Yeah, you definitely want that. You should get this is honestly. We could get all of food. But I feel like if I put them at the same time, they can come.
That happens sometimes, right? We're going to look for, and I have a sketch here, we're going to look for Q exit. Okay. Here's a sketch. Here's a nice box. Here are the sides. And you see those little like indents and stuff?
Yeah, what's that all about?
Those are the components. That's what they're kind of.
Oh,
Yeah.
Yeah.
Yeah. So don't worry too much about that. Okay. Basically, here is our boundary. This is the air inside here. So you see those components? They produce. Oh. No, I just wanted to be that color. There. They produce. Oh my God! Stop it. There. Q in to the air, and they also go out to the exit. Okay? So some of the heat from the circuits go into the air, and some of that goes out to the surroundings. Okay? And that's what we're looking for. All right? Assumptions. Yeah, we're actually trying to figure out what the Q in to the air would be. Okay, does it heat up? Yeah, it heats up 10 degrees C. Okay, so we're going to look for that. So assumptions, we have our steady state, and we can do an ideal gas. So you see how this says the components of the electrical system dissipate 180 watts? That's the total Q, but that's split up into in and external, okay? So in your givens, I put Q dot total is 180 watts. So far, does everyone understand this setup? What's going on here? All right, so let's get right to the solution. So we're going to find Q dot exit, and that comes from this. So the total dissipate energy is split up into going into the air, and the other goes out to the surroundings. Okay? So we're looking for Q dot exit, which is the Q dot total, which we have, subtract Q dot in. And then how do you think we find Q dot in? We use the First law, okay. So find Q dot N. Oops, where do you write that? Oh, so let's just write the first law. So we have 0 equals Q dot, and this is the first law on the air. So Q dot in minus Q dot out plus W dot in minus W dot out plus summation of M dot, and this is N, which would be H, plus V2 squared over 2 plus GZ minus out M dot H plus V squared over 2 plus GZ. So we're only looking at the air inside that duct. What did we assume? It's just Q coming in, right? So there's no Q out of the air. It's only coming in for Q. There's no work or power at all, right? And velocity is the same diameter pipe, and the elevations, if we pick the center line, they're gone. So we end up with 0 equals Q dot N plus M dot 1 H1 minus M dot 2 H2. So let me just rewrite this. So Q dot N becomes what? The M dot 1 H2 minus M dot 1 H1. I just switch the signs. Oh yeah, M dot 2. Thank you. Oh. This is 2. Yeah. That's 1. There we go. Thank you. And I'm okay now if you go on the side and say conservation of mass. Just M dot in equals M dot out. That means M dot 1 equals M dot 2, which is M dot. So Q dot N equals M dot H2 minus H1. And then air is ideal, so what can we do with H2 minus H1? Change it to CP T2 minus T1. So if you have a section of pipe and you want to figure out how much Q is going in, if you know your temperature differences and it's an ideal gas or liquid, that's the equation right there. We just derived it from the first law of thermal. Okay, so Q dot N equals rho times V dot times CP T2 minus T1. Q dot N, I'm gonna add ideal gas, B over RT, V dot CP T2 minus T1. And we'll use P1 and T1 there. Is the density going to change at state 2? It should, but we're going to assume not. Okay? All right, so it's going to be pretty close for this little section of duct we're looking at. The density of the air is not going to change that much. Okay? All right, so Q dot N equals 101.325 pascals divided by 287 joules per kilogram K times 30 degrees plus 273 times 0.6 meters cubed per minute times 1 minute over 60 seconds times 1005 joules per kilogram K times 40 degrees minus 30 degrees. Whew. Finally, Q dot N to be 117 watts. And to go back to what I was saying with the density, is the mass flow rate, this m dot, is always the same, right? So you can figure the m dot at 1 and then m dot at 2, okay, and they're going to be the same. So, and then finally we can solve for what? The exterior. Yep. 180 watts minus 117 watts. So these components spit out 63 watts to the surrounding. And they do these. This is a quick, like this, using this analysis to get an idea of what's happening. They do quickly. This is a quick estimate. And then they can go in and get more details, okay? And do more heat transfer analysis to figure out how can we fix this, okay? CP of air is 1,005 joules per kilogram, okay, or 1.005 kilojoules. Okay, so air at 30 or 300K and 100 kilopascals steadily flows into a hairdryer having an electric work input of 1,500 watts. Because the size of the air intake, the inlet velocity of the air is neglected. The air temperature and velocity at the hairdryer exit are 80 degrees C and 21 meters per second. All right, the flow process is constant pressure and adiabatic. Assume air has a constant specific heat at 300K, which is the values we've been using. Determine the mass flow and the volume flow. Okay. So what does the adiabatic mean? There's no Q going through the boundary, correct? So given P1, this one we'll just do 100 pascals. Make it easier. T1, 300K. Unless it, did it say? Oh, okay. So we'll do that then. I thought they said atmospheric, but V1, they said make it 0. Which, have you ever felt behind your hand in a fan and then in front? Like it's really slow in the back, but it's significantly higher in the front, okay? So that's a good approximation from experience. T2 and V2. And all that speed has to do with the props, right, on the fan. They're angled and they're curved to help force the air. Math and science. Yep. We have an electric input of 1,500 watts. We're going to find M dot and V dot, right? See how I'm doing this problem nice and neat with units?
No, I'm just
I wasn't. Students that here on Wednesday. Assumption, steady state, adiabatic, Q is 0. Sketch. Yep, and that's what I'm going to do. Some of you did. Some of you actually took. I think it was Wesley. He actually printed, put the computer paper in the printer and printed the sketch. I'm fine with that. I think dynamic students, they do that. I'm okay with that. Some of you guys, I don't know if you guys have done it, but let's see. Where are we looking here? We're looking right here. 1, 2. And I also made it properties. CP 1005 joule per kilogram K, and R is 287 joules per kilogram K. All right, first law. 0. This is N minus. Hopefully you memorize this by now, right? It's almost similar to what we've been writing in fluids, right?
Yeah.
So many fluid students, but you're not in fluids. Not yet. Maybe we can convince you to stay. We can cancel this velocity, right? We said that was 0. Let's cancel the altitudes. There's no workout, and it's adiabatic. So we end up getting this from the first law. Conservation of mass. N equals out. M dot 1 equals M dot 2. M dot. So that simplifies this to blah, blah, blah. Let's see. N plus M dot. This would be H1 minus H2 minus V2 squared over 2. And then I think we can solve for mass flow. So M dot equals minus 1500 watts over 1005 joules per kilogram K, 300 K minus 80 plus 273 minus 21 meters per second squared over 2. Just zoom back out real quick. You still see that all right? Wait, I'll do this up here. Now, if you think about it, if we go back up, and I'll come back down here to our red equation here. What did we assume velocity 1 was? 0. So another value that would be acceptable is if you just got rid of that one, right? Because mass flow is rho AV, we assume the velocity is 0. You get a different number, okay, but it's still a valid assumption of what you're doing. Okay, a lot of the times these values give you like an ideal kind of case, okay, a rough idea of where to go or how to start something, and then you just evaluate that further, okay? And we'll talk more about that when we get into the second law and things you can do to help this, all right? This is the mass flow, and the last thing was volumetric flow. Okay. So V dot 2 is A2 times V2. We also know that M dot 2 is rho 2 V dot 2, right? So those two equations, we know we can somehow find volumetric flow rate. If we don't know the area, then we should use the other one, which is we know the mass flow over the density. So the mass flow, I think we found to be m dot. And then how do we find density? Ideal gas, yep. So I have P2 over T2 times R. So it's kind of written weird, but so m dot T2. Why do you keep going away? And I'll just do it over here to save some space. 0.028 kilograms per second, 287 joules per kilogram K, times 353 K over 100,000 pascals. So we get 0.0284 meters cubed per second. What was the mass flow? 1.028. So pretty close, because the density of air is pretty close to 1. So